By the mid-1970s, Intel had established itself with the 8080, an 8-bit microprocessor that helped spark the personal computer industry. The company was also finishing work on the 8086, a 16-bit chip that would extend that same basic lineage. But inside Intel, there was a sense that these designs, however successful, were fundamentally limited. They were built by extending older ideas rather than rethinking what a processor should be. So, around 1975, Intel began a far more ambitious project, internally known as the 8800, and later renamed the iAPX 432. The goal was not to build a faster version of what already existed. It was to design an entirely new kind of computer from first principles, one meant to leapfrog the entire industry rather than compete incrementally within it. Intel wanted a processor built for the software of the future, not the software of the past. The iAPX 432 was conceived as what Intel called a micro-mainframe, a microprocessor with the sophistication of a mainframe computer system. Its most distinctive feature was that it was object-oriented at the hardware level, decades before object-oriented programming became mainstream in software. Every piece of data in memory carried a tag identifying its type, and access to it was controlled through hardware-enforced capabilities, meaning a program could only touch the objects it had explicit permission to use. This was capability-based security built directly into silicon. The chip also handled memory management automatically, allocating and protecting memory without relying on the operating system to police it manually. The pitch was that future software, especially in high-level languages like Ada, would be more reliable and easier to run safely across multiple processors, because the hardware itself would prevent entire categories of bugs and security violations that plagued conventional systems. In practice, the 432's sophistication came at a steep cost. Checking tags and capabilities on every memory access consumed enormous amounts of processing time, and the object-based addressing scheme meant that even simple operations required extra steps compared to conventional processors. The chip itself was split across 2 and later 3 separate physical dies that had to communicate over a bus far slower than the logic inside them, creating a bottleneck no amount of clever design could fully hide. Compounding this, the software tools were immature. Intel expected most 432 code to be written in Ada, a language still new and lacking mature, optimized compilers at the time. The compilers that did exist often failed to generate efficient code for the 432's unusual instruction set. When independent benchmarks eventually appeared, the 432 performed far slower than contemporary chips, by some estimates several times slower than Intel's own 8086, though exact figures are disputed and likely varied by workload. Intel finally brought the iAPX 432 to market in 1981, after several years of delay. That timing proved disastrous. That same year, IBM released the IBM PC, and its choice of processor fell not on the 432, but on the 8088. A variant of the very 8086 architecture, the 432 was meant to render obsolete. The personal computer market that would come to define the industry was built on the architecture Intel considered its stopgap, not its flagship. Meanwhile, the 432 struggled to find a home elsewhere. Its performance problems made it unappealing for general-purpose computing, and the ecosystem of compilers, operating systems, and third-party software it depended on never matured enough to attract developers. Intel continued limited development for a few more years, but by the mid-1980s, resources and attention had quietly shifted toward refining and extending the x86 line, the very lineage the 432 had been designed to replace. The iAPX 432 never achieved commercial success, and today it survives mainly as a case study in computer architecture courses. Cited as an example of how ambitious design goals can collide with the practical realities of hardware performance and software readiness. Whether it directly influenced later systems is genuinely debated among historians and engineers. Some point to conceptual echoes in later protected mode designs and in academic object capability systems, while others argue the 432 was largely a dead end, whose ideas were reinvented independently rather than inherited. What is not disputed is the irony surrounding it. While Intel poured resources into a processor meant to define computing's future, the x86 architecture it treated as a temporary bridge became the accidental backbone of personal computing for decades, a dominance built less on elegant design than on timing, compatibility, and the momentum of the market it happened to capture first.